Okay, so now till now what we have discussed, the three main important systems. One is translational mechanical systems, rotational mechanical systems, and electrical systems, and a sort of combination. Now we will do the electrical analogous of mechanical translational systems. The systems remains analogous as differential equations governed by the systems or transfer function are identical forms. So there are, we wanted to do in two ways. One is force voltage analogy and force current analogy. How? And we'll see in this particular session. So in this session, what you do here, you can see. Suppose you have a mechanical system. So what is analogous to electrical systems? So let us take. Suppose this is mechanical system. What is its analogous to electrical system? So in the mechanical system, the input is force, the output is velocity, right? In electrical system, because we are telling about the voltage analogy, force voltage analogy, input is the analogous to the force. Here it is the voltage, analogous to the velocity is the current, that is d I equal to dq by dt. Okay, so current, that's all it is. So we basically these are the two items. Now let us see and then draw it. Suppose we are drawing a friction coefficient, that is B. So that we already know the friction coefficient B is been given, and here we are giving the force F. Now this can be written as F is equal to B into dx by dt. So assuming that here it is displaced by a distance x. Similarly, what is the analogous to its electrical systems? So here the force, as I was telling, it should be replaced by a voltage source, and the the friction coefficient analogous in electrical systems is the resistance, right? So now here the current is I and the voltage is say E. Now E is equal to I into the resistance is R. That simple it is. Similarly, if you take the mass, okay, the mass portion here, the mass here I am giving F, I am giving the mass, okay. So this M, and I am maybe certain reference that we are doing here. So at the time what we have written, F is equal to, and again the displacement is same, x M into d square x by dt square. It is something di by dt form. Where is the di by dt form comes? It is in the inductance. So again the voltage source followed by a inductor. So this inductor is L. So the voltage drop across the current, that is again say I. The voltage drop across this way we can call as E is equal to L into di by dt. So here how do you see this? So here dx is coming directly, I is coming. So if I write this particular thing, dq by dt, I is equal to dq by dt. Here also I is equal to dq by dt. It will become d square by dt square into q. So they are, I mean, the equations are very clear in terms of how the system is being represented. So for the spring, the force that we are giving onto the spring, and assuming it is fixed at what I mean reference, so and this is displaced by x, and the force that you are giving is F. So F is equal to k into x. So here what is the thing? So here it is equivalent to the capacitor. How it is capacitor? So it is very simple. Here the I, this is E. So E is equal to whatever the voltage 1 by C integral I dt. I is equal to dq by dt. So integration cancels. So what I mean you will get. So integration q by c only you will get. That's all. So if you write in terms of q, integral dq by dt into dt. So integration differentiation cancel. Finally, you'll get only q by c. That's all. So that is how you can write the equations in this analogy form. Okay. So here as I was telling you, in terms of force current analogy, so the same system, it is voltage, input sources is voltage, output is current. Output is the current. Here in the electrical system, it may also happen that input is current source, output is the voltage across the element. So similarly here, the equation only the you know representation, the current instead of voltage source, the current source will be there, and voltage across the element that we are writing here. So I is equal to V by R. Similarly, the mass here again different. The mass here in the current analogy is a bit different compared to there. Here the mass is in terms of capacitor in the current analogy. Reason being, I is equal to C dV by dt. So we are writing in terms of the total current I it is following. So similarly, it is some sort of an analogy if we are taking voltage, and this will be interchanged with each other. So here the L, so I is equal to 1 by L integral V dt. So these are the things that you need to keep in mind when you are talking about the voltage current analysis or current voltage analysis. So it is very simple. Now let us do one small exercise and then we'll get a crystal clarity on it. So let us write the differential equations for the mechanical system. So we'll draw it force voltage and force current analogous circuits, and then we'll verify by the mesh and node equations, right? So let us take one particular equation and then try to solve those things. So here, so I'll do that. So here the mass is m1, it is connected to a system like this, and there is another system, say this is m2, it is connected to another system, let me assume like this, and it is connected to some sort of a reference. So I'll take this also as a reference. So here the friction coefficient is say B1, and here I am giving certain amount of force F of t. So here the displacement is happening x1, here the displacement is happening x2, the coefficient, this one I am taking as k1, the coefficient I am taking as b12, the coefficient here this k2, and this is b2. So all are simple, whatever we are trying to do, the same thing we are trying to write, the similar force voltage, force current, all those equations. So the first come first, what we have discussed in our earlier systems. So what we have discussed, so we discussed that the equations, how these things are there, the free body diagram, that is the force acting on the mass m1 plus the force acting on the b1 f b1 plus f b12 plus f k1 is equal to f of t. So if I write the equations for it, that is m1 into d square x1 by dt square plus b1 into d x1 by dt plus b12 into d by dt of x1 minus x2 plus k into x1 minus x2 is equal to f of t, right? So similarly the mass diagram for, if you write for the mass 2, so I'm just making it simple, change nothing else. So for the mass 2 free body diagram, if I write, that is f m2 plus f b2 plus f k2 plus f b12 plus f k1 is equal to 0. So simple, in the mass m1 this f, this b1, this b12, this k1 are acting. In the m2 b12 k1, k2 b2 are acting. So that is how we can simply write those things. So these equations can be written as m2 d square x2 by dt square plus b2 dx2 by dt plus k2x2 plus b12 d by dt of x2 minus x1 plus k1 into x2 minus x1 is equal to 0. That's all, very very simple things, equations. Now we will write when we are trying to replacing the displacement by velocity, we will write the equations as something like this. So what we do, already that velocity is equal to dx by dt, right? And its d square x by dt square is acceleration, that is dv by dt. Now and x, if you want to find, x is equal to integral v dt from this. So applying these concepts into this, what you will get, in the m1 dv1 by dt, velocity I am writing, plus b1 v1 plus b12 v1 minus v2 plus k1 integral v1 minus v2 into dt is equal to f of t. Similarly here m2 dv2 by dt plus b2 v2 plus k2 integral v2 dt plus b12 v2 minus v1 plus k1 integral v2 minus v1 into dt is equal to 0. Okay, so that these are the very very simple things. That's how we have designed. Now how do we convert the given mechanical system which is analogous to the force voltage system? So in this one, the important thing that you need to bring up your mind is, here there are two masses, that means two nodes will come into picture, and these two nodes, how are we representing? So from our earlier analysis, so what we can think of it is, f of t is equal to generally the force that we are applying. m1 is L1, m2 is L2, and b1 is R1, B2 is R2, B12 is R12, resistance between 1 and 2, K1 is 1 by C1, K2 is 1 by C2, and whatever the V1 velocity 1 I am writing as I1, velocity 2 I am writing as I2. So that is how, simply I am just putting those into these things here. Those way you can able to do that analysis. So considering those analysis, so I can write this complete system equation as something like this. So there is certain voltage that I am representing as E of t, and the inductor, so there is a L1, that is M1 means L1, that is B1 means R1, and there is a resistance that exists between these two. That resistance we are calling as R12, and the capacitance we are calling as C1, and these are connected here, and that is connected to L2, R2, and then C2. This is the equation that we are trying to get. So for this particular circuit, so if you correctly analyze, so f of t, whatever that we are giving, this f of t is corresponds to the e of t. M1 is L1, so here B1 is R1. Now the K1 and B12 are sandwiched between M1 and 2, so K1 and B12 are sandwiched in M1 and M2, and this L2 is K2, and here again the same thing will happen between these two. It is R2, C2, and these things will come into picture. So now what will happen, if I mean, you can, from this particular circuit you can draw the equivalent circuit for it. Okay, equivalent equations for it. So the above equation. So here equivalent circuit E of t is equal to L1 di1 by dt. So I'm just writing the equation for this particular loop, right? Plus R1 I1 plus R12 I1 minus I2 plus 1 by C integral I1 minus I2 into dt. So for the second loop, if I draw the, if I write the equation, so I'll start from here. That is L2 d I2 by dt, L2 di2 by dt plus R2 I2 plus 1 by C2 integral I2 dt plus R12 I2 minus I1 plus 1 by C1 integral I2 minus I1 into dt is equal to 0. So that is how you can draw the force voltage analogous circuit for the system. Similarly, if you want to write the force current analogous system, so you should know the parameters. What are the parameters? Here the force is equivalent to the current, f of t is equal to I of t. M1, so wherever the M1 is replaced by L1, it will be M1 is replaced by C1, and B1, here at the time it was a resistance, now it will be admittance. Now K1 is 1 by L1. So similarly K2 is 1 by L2, B2 is 1 by R2, M2 is C2, B12 is 1 by R12. So here where the voltage, the velocity is V1 and velocity is V2 and all those things. So here also you can, same thing you can replicate. So I'll just take this equation. Here also what you can do, so you can take this entire thing. I'll take entire thing and then take, so let me take this. Yeah, so I'll just copy it. So I'll just paste it in the new page so that we can freshly start for the analogy. So easily we can understand this. So for this particular figure, right? So whatever we are writing, so the same thing we will write here. The for this particular system with the above analysis, it is current I, and the here the L1, I mean here the M1 is C, the resistance is 1 by R. So like that is that much simple it is. So we should just know what are the things that we need to write, and then this is exist between both of them, that is R12 and L1. It is something, it is also called duality. So right, this is C2 R2 L2. So this is I of t, C1 R1 R12 L1 C2 R2 L2. Here again the same nodal equations V1, nodal equations V2. If I write, I'll write the equations for both of them in terms of KCL. So what I'll write, current, okay, C1 dV1 by dt, the incoming current equal to outgoing current, right, plus 1 by R1 V1 plus 1 by R12 into V1 minus V2 plus 1 by L1 integral V1 minus V2 into dt is equal to the total current I of t. For the, so we have written only for till now here. Now we'll write from for this particular node. Here C2 dV2 by dt plus 1 by R2 V2 plus 1 by L2 integral V2 into dt plus 1 by R12 V2 minus V1 plus 1 by L1 integral V2 minus V1 into dt is equal to 0. So that is how you can able to draw both the force voltage, force current analogy for the given circuits. So this is how you can draw the force voltage analogous circuit, force current analogous circuits for the given mechanical system. So now you have studied the entire, the rotation translational mechanical system into force voltage, translational mechanical system into force current, all those things that you have clearly understood.